September 2025. NASA tracks something unprecedented. Interstellar Comet 3 I/ATLAS, traveling at 137,000 miles per hour, was struck directly by a coronal mass ejection. Within 72 hours, two novas erupted in the southern sky, bright enough to see with naked eyes. Venezuela experienced twin magnitude 6 earthquakes. Statistical analysis reveals these events occurring together has less than 0.1% probability. Scientists have named it the 72-hour complex. Could an interstellar object passing through our solar system be connected to Earth's geophysical responses? Let's dive right in. On the night of September 22, 2025, Australian astronomer John Seek was scanning the southern sky when he detected something that made him immediately alert observatories worldwide. A new star had appeared in Centaurus, except it wasn't new at all. V1935 Centauri, a white dwarf star in a binary system, had just detonated. Within minutes, gamma-ray observatories Fermi and Swift confirmed what Seek suspected. This was a classical nova, a thermonuclear explosion on the surface of a dead star. Here's how it works. For decades, the white dwarf had been stealing hydrogen from its companion star. That fuel accumulated, compressed under immense gravity until reaching critical density. Then fusion ignited, not gradually but explosively. The blast hurled material into space and flooded the cosmos with high-energy radiation. In just 3 days, V1935 Centauri brightened from magnitude 10.2 to 5.8, visible to the naked eye. For reference, naked-eye novas typically appear once every few years, sometimes once a decade across the entire sky. But this was only day one of something far stranger. September 23rd, less than a day and a half after V1935. Centauri exploded, Dr. John Seek made another discovery that stopped astronomers in their tracks. V799 for Sagittarii had ignited in the constellation Sagittarius, the region pointing toward our galaxy's central supermassive black hole. Another classical nova, another white dwarf detonation, another gamma-ray burst confirmed by multiple observatories. At magnitude 6.2, it was visible through binoculars from anywhere in the southern hemisphere. 2 naked-eye novas within 36 hours. Astronomers immediately checked historical records. Computer databases were queried. Colleagues across institutions compared notes. The consensus, this simultaneous pairing, was exceptionally rare. But no one realized yet that this was part of something larger. At 4:47 a.m. local time on September 24th, northwest Venezuela was struck by a magnitude 6.0 earthquake. Buildings swayed. Residents evacuated into the streets. Emergency services mobilized. Then, less than 6 hours later, it happened again. Another magnitude 6.0 earthquake hit the same region, followed by a strong aftershock. Seismologists immediately pulled historical data for this area. Northwest Venezuela sits on an active fault system, but earthquakes of magnitude 6 or greater typically occur once every 2 to 3 years. 2 within 6 hours? The data showed this was highly unusual, even for a tectonically active zone. What seismologists didn't know yet, because they don't typically coordinate with astrophysicists, was that these earthquakes were unfolding during the exact same 72-hour window as the 2 stellar explosions. And there was one more event occurring simultaneously that would tie everything together. While Venezuela was shaking and stars were exploding, NASA's Solar Dynamics Observatory was tracking something unprecedented 100 million miles away. 3 I/ATLAS, an interstellar comet from beyond our solar system, only the third ever confirmed, was racing toward its closest approach to the sun at 137,000 miles per hour. NASA's models detected a massive coronal mass ejection, CME, on a collision course with the comet, not a near miss, a direct hit. Coronal mass ejections are solar storms, billions of tons of magnetized plasma hurled from the sun's corona at speeds exceeding 1 million miles per hour. When they strike Earth, they can disrupt satellites, knock out power grids, and create spectacular auroras. But a CME striking an interstellar comet? That had never been directly observed. The models predicted impact within an 8-hour window centered around noon UTC on September 24th. right as the Venezuelan earthquakes were happening, right as two novas were blazing in the southern sky. The CME slammed into 3I/ATLAS, exactly as predicted. Observatories worldwide turned their instruments toward the comet to capture what happened next. 3I/ATLAS had already been behaving strangely. Weeks before the CME impact, it had mysteriously brightened by a factor of 20, jumping from magnitude 16 to magnitude 12. Most comets brighten as they approach the sun, then fade predictably. But 3I/ATLAS wasn't fading. After the CME struck, its brightness remained elevated. Then came the observations that puzzled astronomers. Professional telescope arrays recorded the comet's plasma tail pointing away from the sun, exactly as expected, since solar radiation pressure pushes comet tails anti-sunward. But amateur astronomers using smaller telescopes reported something different. Portions of the tail appeared to push sunward toward the sun. That shouldn't be possible under conventional models. The CME had fundamentally altered the plasma environment around 3I/ATLAS. Its dust coma, the cloud of gas and particles surrounding its nucleus, expanded to enormous size. Ionization continued for days as charged particles from the solar wind interacted with the comet's material. Despite weighing 33 billion tons, the comet's trajectory through space remained unchanged, but its appearance and behavior had transformed into something astronomers struggled to explain with standard comet physics. Astronomers began comparing notes across disciplines: two novas, twin earthquakes, a CME striking an interstellar comet. All within 72 hours, statistical physicists ran probability calculations. What are the odds of these four independent events clustering within the same 3-day window? The answer: less than 0.1%, 1/10 of 1%. In statistical analysis, this is called Poisson clustering, when rare independent events bunch together in time or space. It happens occasionally by pure chance, but the probability of clustering this dense is extraordinarily low. This wasn't just unusual, it was a statistical outlier of the highest order. The scientific community gave it a name: the 72-hour complex, or the 72-hour event stack. And it immediately sparked debate that continues today. Is this coincidence? Or is something connecting these events? Mainstream science favors the coincidence explanation. In an infinite universe with countless events occurring constantly, even 1 in 1,000 combinations must occasionally happen. The 72-hour complex could simply be an extraordinary roll of cosmic dice, but a subset of researchers is asking uncomfortable questions. Could there be mechanisms we don't understand linking solar activity, interstellar objects, stellar explosions, and seismic events? 3I/ATLAS displays characteristics that don't fit conventional comet models. Its dust coma has surprisingly little gas emission. Its tail has been observed pointing sunward, opposite to what solar radiation pressure alone should produce. Its orbit threads unusually close to the ecliptic plane, passing near Jupiter, Mars, and Venus in direct alignment with the sun's magnetic field lines. Some researchers point to electric comet theories, models proposing that electrical and plasma interactions in the solar wind environment can shape comet behavior in ways that gravity-only physics can't explain. As an interstellar object, 3I/ATLAS may carry different electrical properties than comets born in our solar system. Its passage through the heliosphere, the sun's magnetic bubble, could potentially create electromagnetic disturbances. This remains highly speculative and controversial, but the observations are real. During the 72-hour window, the sun was in an active phase. Solar cycle 25 was approaching maximum, with numerous sunspots, elevated solar flux, and dynamic solar events. Solar wind density fluctuated significantly. Some researchers have proposed, controversially, that variations in solar wind and geomagnetic conditions might influence Earth's electromagnetic environment. In theory, changes in the magnetosphere could add stress to tectonic fault lines, particularly in regions already near their breaking point. The proposed mechanism, electromagnetic variations, might alter crustal stress patterns or trigger piezoelectric effects in quartz-rich rock. If a fault is already primed to rupture, even small additional stresses could potentially advance the timing. Mainstream seismology remains skeptical. Earthquakes are driven primarily by tectonic plate mechanics, but the temporal correlation during the 72-hour complex has drawn attention from researchers willing to explore unconventional hypotheses. Here's what we know for certain. 4 statistically rare events occurred within 72 hours. The observations are verified by multiple independent sources worldwide: professional observatories, amateur astronomers, seismic networks, and NASA spacecraft. The probability calculation of less than 0.1% is mathematically sound. What we don't know, whether any causal connection exists between these events. The 72-hour complex provides researchers with something invaluable: a natural experiment. Gamma-ray data, X-ray emissions, seismic readings, solar wind measurements, and comet observations were all recorded in unprecedented detail during this window. Scientists are now analyzing terabytes of data, searching for correlations. Did gamma-ray emissions from the novas coincide with any measurable changes in Earth's magnetosphere? Did solar wind fluctuations show unusual signatures during the earthquakes? Did 3I/ATLAS exhibit electromagnetic anomalies before the CME impact? This event exposes fundamental gaps in our understanding. We know solar activity affects Earth. Geomagnetic storms are well documented. We know novas occur regularly in our galaxy. We know earthquakes follow tectonic cycles. But we don't fully understand how these systems might interact across vast distances. Could the solar system be more interconnected than current models suggest? Could electrical and magnetic circuits link the sun, planets, comets, and even distant stellar events? Or is the 72-hour complex simply proof that in a probabilistic universe, even the near impossible must occasionally occur? 3I/ATLAS has passed perihelion and is now heading back toward interstellar space, never to return. The 2 novas are fading as their explosive outbursts dissipate. Venezuela's seismic activity has returned to baseline levels. The 72-hour window has closed, but the questions it raised are just beginning to be investigated. Research papers are being prepared. Data is being cross-referenced across disciplines. Astrophysicists are collaborating with seismologists, space weather researchers, and statistical physicists in ways they rarely have before. The scientific method demands skepticism. Correlation doesn't prove causation, but it also demands we investigate anomalies when they appear, especially ones this statistically extreme. The 72-hour complex represents exactly the kind of outlier that can either confirm our existing models or force us to reconsider them entirely. So what does the 72-hour complex actually tell us? It reveals that our solar system may be far more interconnected than we realize. 4 statistically rare events, less than 0.1% probability, occurred simultaneously, and we still can't definitively explain why. This matters for the future of space exploration. As NASA plans crewed missions to Mars and establishes lunar bases, understanding how solar activity, interstellar objects, and electromagnetic environments interact isn't just academic, it's critical for mission safety. If a CME can fundamentally transform an interstellar comet's behavior, what else can it affect? 3I/ATLAS has left our solar system, but solar cycle 25 is still approaching maximum. More solar storms are coming. More interstellar visitors will pass through. Scientists are now developing enhanced monitoring systems specifically because of what the 72-hour complex revealed. Here's my question. Do you think this was pure coincidence, or is there a connection we haven't discovered yet? Drop your thoughts in the comments. I read everyone. This is Space Hub, where we analyze the space events that challenge what we think we know. If you want more deep dives like this, hit that subscribe button and turn on notifications so you don't miss the next breakthrough. Like this video if the 72-hour complex surprised you as much as it did scientists. The universe just showed us how much we still have to learn, and we're just getting started. China just announced reusable rockets to challenge SpaceX. Bold move. But here's what the data reveals. SpaceX has landed over 500 boosters, with some reflying 20-plus times. China? Still testing prototypes with 0 operational reusable rockets. The numbers are brutal. SpaceX carries 85% of the world's orbital payload. China launches dozens of rockets yearly, all expendable. And by the time China fields its first reusable rocket in 2026, Starship will have already changed the game completely. This is about economics. SpaceX, $2,700 per kilogram. China, locked into expensive, single-use hardware. The gap isn't closing. It's widening with every Falcon 9 landing. Let's dive right in. To understand why China is struggling, we need to start with what made SpaceX's breakthrough so devastating. Before 2015, every rocket launch meant discarding tens of millions of dollars of hardware. Launch once, throw it away? The space shuttle tried reusability, but was so complex and expensive that it actually cost more than expendable rockets. Falcon 9 changed the equation. When that first booster landed successfully in December 2015, it proved something critical. You could bring a rocket back, refurbish it, and fly it again, profitably. That single achievement transformed space launch from an expenditure into an investment. This is the revolution China missed in real time. While SpaceX was perfecting this capability through years of testing, crashes, and incremental improvements, China's space sector was focused on expanding its expendable rocket fleet. By the time Chinese officials recognized reusability as essential, SpaceX had already completed over 100 successful landings. That timing matters more than most people realize, because reusability isn't just a feature you can add to a rocket. It requires fundamental design choices from day one. Chinese engineers have access to videos of every Falcon 9 landing. They can study technical papers, analyze trajectories, and examine the basic principles. So why haven't they replicated it? The answer lies in understanding what reusability actually demands. A reusable rocket needs extra fuel to slow down and return. That's propellant that could have been used for payload. SpaceX solved this through precise engineering. Stronger fuel tanks to handle the extra load, more efficient